By the way, how long are these talks supposed to be? 15. That's good. I don't have much to say. Yeah.
I convinced you.
Yeah. Yeah, what I'm going to talk about here is a fairly simple mathematical investigation that I'd been thinking about for quite some time and kind of doing back of the envelope proofs for, and then the announcement of this workshop caused me to write up a very simple version of it, and I'll talk a bit about that and then about the more complex versions that I would like to do. So the basic question here was, we know from a long time ago from the work of Cox in the 40s or 50s or whenever that was, and similar work of De Finetti before that if you assume some basic axioms about consistency and coherence of reasoning, then you can get probability theory to fall out of those axioms. And then one of the arguments people have against the cognitive relevance of this is, well, okay, but no real mind can ever be fully consistent and coherent in the real world, and therefore that argument in favor of probability theory is irrelevant. And the counter-argument to that you'd like to make is, okay, but even if you want to be just approximately coherent and consistent, then that should mean you have to approximately follow probability theory. And that's almost obvious, but not quite obvious enough for the skeptics. So you want to go through and do calculations in that regard. And here I did some simple calculations for one of the axiomatic formulations of coherence and consistency, and got partway through doing it for some of the others, but didn't put it in this paper. So the basic answer is yeah. I mean, if you're approximately consistent and coherent, that means you're approximately following the rules of probability in your inferences. So I'll explain a bit of that story here. So the basic idea underlying Cox's axiomatic foundation for probability theory was, if you assume probabilities are real numbers, and you assume if you assume plausibilities as your generic measurement of uncertainty are real numbers, and if you assume that plausibilities obey a few basic commonsensical rules, like defaulting to Boolean logic in the case of absolute truth or falsity, and if you assume that plausibilities must be consistent in a certain sense, you can derive from that plausibilities are some monotonically scaled version of probability. And the specifics of that were a bit more detailed, and unfortunately those of you in the back of the room can't read that. But I made most of these slides before I knew the human factors of the room. But the basics are, Cox assumed a simple axiom about negation. So the function mapping the plausibility into the plausibility of its negation, if you compose it, you get the identity. And the plausibility of a conjunction depends only on the plausibility of the conjuncts. And if you have two different ways to get to the same conclusion, the plausibility should come out the same no matter which way you follow. So if A and B is equivalent to C and D, if you get the plausibility of A, get some more evidence, get the plausibility of B and put them together, it should give the same as if you do it for C and D. And this is the axiom that has seemed counterintuitive, because, of course, in a real mind, that's not true. If there's two different routes to get to the same conclusion, we may not assign the same plausibility to both of those conclusions as human beings, because we don't have infinitely powerful minds and we get confused and do stupid things. So these axioms are too strong to apply with full accuracy to a real system like the human mind, or even to a Bayes net or something that makes certain approximation assumptions. What Cox showed is that they lead to the conclusion that the plausibility is some monotonically scaled version of the probability, which was a very nice conclusion. I mean, it was a bit naive in the way the proof was done, so Cox's proof actually assumed more. It assumed differentiability of the plausibility, and later people went through a lot of work to get rid of that assumption and replace it with more complicated things and some more elegant things quite recently. Now, there's a recent paper by Dupré and Tipler, which is the same Tipler, incidentally, who has posited the omega point at the end of the universe, when the universe will achieve infinite algorithmic information and all possible realities will happen. But this is a more rigorous piece of mathematical work on his part. And given that this is a short talk, I don't think there's not even time to read all the detailed axioms of this approach, but they are in the paper in the proceedings. But in essence, I felt that you should be able to take any of the multiple axiomatic derivations of probability theory and make the axioms, rather than precise, make them probably approximately correct. Like the probability is greater than so and such, that these axioms hold within error epsilon. And then you should be able to conclude that reasoning follows the probabilistic axioms in a probably approximately correct sense. And since I'm very busy with other things, I carried out that calculation for the simplest axiomatization of probability theory that I could find, which was Dupré and Tipler's, which is sort of order theoretic. It's not actually my favorite derivation, but it's simple to go through the calculation. It's sort of a prototype for other results along the same line. So they make assumptions that you can kind of take a plausibility value and do a kind of scalar rescaling of it, similar to a temperature value or anything else you're measuring. They assume that order is consistent, and their axiom 4 is the analog of Cox's main axiom, the one which was third on my list. So the kind of cognitively non-trivial axiom here is that getting to the same conclusion by multiple routes is going to give you the same answer. And Dupré and Tipler's axiom 4 is basically like that. So they assume as a function of x, this plausible value of x and e given c depends only on the plausible value of x given e and c. So that's basically assuming that what order you consider the evidence in doesn't influence the answer you get, which is cognitively dodgy, because for humans, or for OpenCog for that matter, what order it gets the evidence in definitely can influence the conclusion it gets. So it's not absolutely right for any real mind. But from these axioms, they basically derive rules of probability. I mean, the hard part is deriving this rule, which is shown there, which is a kind of multiplication rule for conditional plausibilities, and showing it's a probability. And what's done in the paper, basically, I replace their axiom 4 with a hacked axiom that has probabilities all over the place. So instead of saying these two different ways of getting to the same answer are equal, you say the two different ways of getting to the same answer are equal within epsilon, with a probability greater than 1 minus delta. So you're probably approximately sure to get to the same answer if you approach it by considering evidence in two different orders. And if you assume that, what you arrive at, not very surprisingly, is that this product rule for conditional probabilities is probably approximately right for you. And you can get the same thing with the approximate additivity of plausible value. You can get it so that it approximately works. And if you're curious about these calculations, they're in the paper, which is an easier way to digest it than looking at it on the screen. So the message from those calculations is, according to the Dupré and Tipler axioms, if the consistency holds approximately, then the plausibilities behave approximately like probabilities. Or, as I almost gave this paper, the paper of this title would decide not to, but probably approximately consistent plausibilities are probably approximately probabilities, right? So that kind of, you can put that on your T-shirt, right? I mean, that's, which again is how you would think. It's how you would think that it works, and it does work. It does actually work that way. Now, what I would like to do next in the spare time that I find for these things, or would be happy for someone else to do, you could do a similar calculation for other axiomatic derivations of probability theory. So I'm particularly, I mean, Cox's original axioms are kind of screwed because they make, I mean, they're right, but they make implicit differentiability assumptions, and people have tried to work around those in very complicated and annoying ways. But Knuth and Skilling had a recent paper called Foundations of Inference that does what I would consider the most elegant axiomatic derivation of probability theory. And I'm not going to go over that in detail now, but their basic axioms are just some extremely simple algebraic axioms on basically the union, which is their plus, a direct product, which is their times, and the composition, which is their circle with a dot in the middle, like chaining of probabilities. So by assuming some extremely simple order theoretic axioms with these operations, they get that any way of assessing plausibility that obeys these basic symmetries must be probability. And I think that's very nice, and I think that you could do a proof on their axioms the same way I did for Dupré and Tipler's. It's just that the proof that probability follows from their axioms involves these fixed point theorems and these functional equations, which are a little messier than Dupré and Tipler's proof, and propagating the probabilities through the fixed point theory is more annoying. So I got lazy and didn't do it. But I'm pretty sure that it's possible, and you would derive the same conclusion here. Another thing that's interesting, but it is a bit of an aside, is if you don't assume plausibilities are real numbers, the whole thing still works. You just get complex number or quaternionic or octonionic plausibilities, which is kind of interesting, from the generalized Frobenius theorem that says those are the only division algebras. And if you take the complex number plausibility obeying all these symmetries, then you can derive quantum mechanics from that, as Sal Youssef showed, and Knuth and Skilling have discussed in some follow-up papers. So actually this all relates to the foundations of quantum mechanics in a sort of interesting way. So like quantum logic takes real number probabilities on a non-distributive, non-Boolean lattice. The other way is to keep the same lattice and use complex number plausibilities or complex number probabilities. And you can do all this stuff there too, which is somewhat interesting. And there may be relations between the foundations of inference and the foundations of quantum theory. But that is a digression for this talk. Now, another kind of theorem that would be interesting to prove, which I have no idea how to prove, but someone else with more time for proving theorems may do in the future. You would like to show that if you have an intelligent system with a certain amount of resources and it wants to achieve some goal in an environment, that system should be trying to keep itself reasonably consistent and coherent, basically. And I think that like OpenCog has to do that. I mean, you can never completely accurately obey these consistency axioms of like always getting the same conclusion if you approach the same problem in two different ways. But you will achieve your goals better if you can approximately be coherent and consistent in that way. And I mean, that takes work. As a human being, it takes work not to become completely irrational. And as an OpenCog system, it does as well. There's cleanup operations it has to do. And I think that is a property of finite resources systems, that they're smarter if they devote attention to maintaining coherence and consistency. And that is because probably approximately being consistent lets you probably approximately obey probability theory, which will let you achieve your goals better in the real world. So this is my way of answering the question, probability theory or not. I mean, I think the answer is yes. I mean, other tools will certainly be useful, and we use fuzzy set theory inside OpenCog for various things as well. But ultimately, I do think probability theory is the right way to think about achieving goals in environments for AGI systems. And a bunch of this axiomatic theory, most of which was developed decades ago, but keeps getting refined by other people. I mean, I think this helps explain why. And that's all.
Thank you very much. Are there any technical questions? Don't ask, we shall approve, please.
Yeah, well, that's the problem with this sort of talk, is you can't actually explain what you're talking about in 15 minutes. So,
Oh, that's
so it goes. Yeah.
Okay, thank you very much. The next speaker is Pei Wang.